And as I said a moment ago, if people have questions, then feel free to just raise your hand and ask while I'm giving the presentation. And this is a joint work with Martin and David, and it's on, so lifetime means in this sense the infinite horizon problem, and it's an investment and consumption under Epstein-Zin stochastic differential utility. So before I talk about stochastic differential utility, I'm going to introduce discounted expected utility. So the problem in that case, the infinite horizon Merton problem, it consists in maximizing the following. So it's just the integral of the discounted utility of consumption here, and u is just some utility function, so concave and increasing. And to do this, the value process is introduced, and that's just essentially the value of the problem starting from time t. So the discounted utility of consumption from time t onwards. And so one such example of a utility function is just going to be the constant relative risk aversion utility function. So this is possibly the most simple, or one of the most simple utility functions, but it looks like this. So if you look at the denominator, when r is less than 1, then it's going to be always positive and concave and increasing. And then when r is greater than 1, then it's going to be always negative and concave and increasing. And in this case, you have an asymptote at 0. So the utility of 0 is essentially minus infinity. So as I said before, the Merton problem, the lifetime problem, is to maximize the following. So why is this a sensible thing to do? Why do we want to maximize utility as opposed to just the consumption? And this is basically because in general, we want to model our agents as having risk-averse preferences. So this means, I guess, if you think about the gamble, so you can either have the sure thing, or you can flip a coin. Heads, you get 0. Tails, you get double. And what this utility function is doing, because of its concavity, is it's saying that the sure thing, or the utility of the sure thing, is going to be, well, in this case, strictly bigger than the utility of the gamble, because the utility of the gamble just is down here. And this is I mean, this is observed empirically, that people do tend to prefer certainty over randomness in this case. So one way of measuring this risk aversion is using relative risk aversion. So we're going to introduce this coefficient of relative risk aversion, r, which is conveniently the same r as we find in this utility function, and that's a measure of how concave the function is, so how averse to risks our agent is. So another way of thinking about this, so let's forget about the randomness for a moment, and suppose that we are just considering deterministic consumption streams. So we can get rid of this expectation, and we can look at this integral, and we can actually define a new probability function, which is on the Borel sets and the positive real line, and it's just going to be equal to the following. So again, because we've got concavity of our utility function, which is c to the 1 minus r over 1 minus r, we're actually going to find that we have, using Jensen's inequality, a sort of, so we have the expected utility of this deterministic consumption stream is actually going to be less than or equal to the utility of the expected value of the consumption stream. And here this expectation is taken to the measure I just introduced, Q. So what this is saying is, as well as controlling our risk preferences, this parameter r is actually doing something else. So it's actually changing the agent's preferences for deterministic consumption streams. And what it's saying in this case is that they prefer a lack of variation over time, as opposed to something that stays roughly constant throughout time. And this is something that we do want to model, and we do want this to happen. But unfortunately, in the case of discounted expected utility, they're both linked in a very strong way. So I'm going to introduce this notion, which is possibly not so known to people, and it's kind of a horrible name. It comes from economics. It's called the elasticity of intertemporal complementarity, which we're going to denote by the letter S. And this is just a measure of how averse to variance over time we are. So think of concavity in the 0 to infinity instead of in omega. And under time additive discounted expected utility, these two are forced to be the same. And this is too restrictive. We ideally don't want to do this. So there's not really any reason to think why an agent's preferences over risky consumption streams should anyway be linked to their preferences over deterministic consumption streams that vary through time. So what we want to do is we want to try and control for these two things separately, and that's what stochastic differential utility is hopefully going to allow us to do. So under stochastic differential utility, the discounted utility function e to the minus delta t times u of c is then going to be generalized to become an aggregator. So you can see that this discounted utility function here does actually fit into this framework, but it's going to be independent of the value of vt, which is the utility process at time t. And actually, in our paper, we go one step further and allow this to be an aggregator random field. So we allow it to depend on omega as well, but for the purpose of this presentation, we don't need to go into that. So we want to define the value process for stochastic differential utility to be instead given by the following. So Vt is equal to the conditional expectation of time t of the integral from time t onwards of consumption aggregated with the utility process. So this, by introducing a nonlinearity here, we're actually going to allow ourselves to separate this risk aversion and this intertemporal complementarity. So that's all well and good, but at the moment we don't necessarily know that this integral on the right hand side is in fact well defined. And so what we're going to do is before we define Epstein-Zin stochastic differential utility rigorously, we are going to introduce this following set of consumption streams. So we're going to define blackboard bold I of G and C, so it's a function of the aggregator and the consumption, to just be all of the continuous semi-martingales V, such that this integral on the right hand side is well defined and finite. So again, we're trying to solve this thing, so we're going to introduce a couple of definitions. The first is going to be a utility process. So if C is a consumption stream, G is an aggregator, then we're going to say that V is the Epstein-Zin, V is just the stochastic differential utility process associated to the pair GC if it's a solution to SDU. And we're further going to say that a consumption stream is G evaluable if there exists such a utility process. And here the key word is if there's a utility process. So at the moment we don't necessarily know that such a utility process is unique. So we're going to denote the set of G evaluable consumption stream C by script E of G. And then again, we're going to denote the set of uniquely evaluable consumption streams. So these are just the consumption streams such that a utility process exists and is unique, and they're going to be denoted by script E subscript U of G. So we got evaluable consumption streams and we got uniquely evaluable consumption streams. And in general, we're going to have this, right? We're going to have that the uniquely evaluable consumption streams are going to be contained in the evaluable consumption streams. And because we're only interested in consumption streams that remain non-negative, that's going to be a subset of the non-negative progressively measurable processes, which here I'm denoting by script P plus. So, okay, this presents us with two issues. So the first one is, what if this is a strict containment? So what if script EU is not equal to script E? So the uniquely evaluable strategies are not, or the evaluable strategies are not all uniquely evaluable. And this is something that crops up, but basically it's going to mean that we have multiple utility processes assigned to any consumption stream, which then means we have to ask ourselves the question, okay, so which is actually the correct utility process in this setting? And another thing that can happen is that the evaluable strategies are actually a strict subset of the non-negative progressive processes. And this basically means we're going to have to restrict the class of consumption streams that we actually consider. So we're going to... Hi, Sigurd?
Hi, yeah. Just asking, so why do you call these things consumption streams and strategies at the same time?
So I guess a consumption stream is just going to be, at the moment, any stream of consumption that we want to assign a utility to. So at the moment, there's no financial market, and we're not trying to finance it in any way. So I guess it's sort of maybe in a second when I introduce a financial market, then we'll see that actually this is something which we want to finance, and we have an optimization problem that we want to solve. So it's sort of a strategy in that sense.
Okay. Yeah. Thanks.
Cheers. So yeah. So if we don't have equality of the evaluable consumption streams with the non-negative progressive processes, then it means that they're actually, when we start to consider our investment consumption problem, there are going to be some consumption streams that we can actually finance, but we can't assign a utility to. And this isn't ideal, really, because this doesn't come from any economic constraint. It actually just comes from an inability to be able to do the maths. So ideally, we don't want that to be the case either. So suppose that a consumption stream is G uniquely evaluable. So there's a utility process and it's unique associated to C. Then we're going to say that the stochastic differential utility of C is just equal to that utility process at time 0, where V satisfies SDU, which was this equation here. And so the investment consumption problem in this case is going to be for some set of attainable consumption streams, which is something I'll expand upon in a moment. But essentially, it means that we can finance them and we don't go bankrupt. And for some set of processes that we can assign a utility to. So notice I didn't say that are evaluable because I've defined that with a very specific meaning. So what we want to do is we want to essentially expand the definition of a utility process later, so that we can actually consider some things that were previously restricted. So given this this set of attainable and something that we can assign a utility to consumption streams, we want to just find the supremum over all of these of the stochastic differential utility. So I'm just going to introduce the market which we're going to be dealing with, which I'm sure many of you have seen before, which is just the Black-Scholes Merton financial market. So you've got a risky asset, which is just given by geometric Brownian motion with drift mu and volatility sigma. And you've got a risk-free asset, which has risk-free rate equal to R. And then so this is sort of what Sigurd was asking. An agent with initial wealth X then has to choose a investment consumption strategy. So that's just a pair of stochastic processes, pi c, where pi t represents the amount that we're investing in the risky asset at time t, and ct represents the rate of consumption at time t. And then the self-financing condition is just going to be the following. So we invest 1 minus pi t times our wealth into the risk-free asset. We invest pi t times our wealth into the risky asset, and then we just consume at a rate ct. And so we're going to say that a consumption or an investment consumption strategy is admissible if this equation is satisfied, the self-financing condition, and that the wealth given by X remains non-negative. So this is saying if we go bankrupt, so if wealth goes to zero, then we're not allowed to invest or consume anymore. And then we're going to define the attainable consumption streams just to be those consumption streams such that we can find an investment process, and the pair pi c is actually admissible. So attainable consumption streams are what we're going to want to maximize over. So if we go back to constant relative risk aversion utility, then the aggregator in this setting is going to be equal to e to the minus delta t times c to the 1 minus r over 1 minus r. And the goal in this case is just to find the supremum over all of our attainable consumption streams of V naught, so the value process at time 0 for that consumption stream. And here we just put it into the so this is what happens if we put the aggregator into the SDU equation. And so one thing that's worth noting here, I guess, is that so some people in the literature, they will actually upcount, so they can consider the utility to be equal to what we've defined times e to the delta t. And then, so the reason that they do this is because it gives a nicer solution to the Hamilton-Jacobi-Bellman equation that arises, and you don't have this this time dependence in there. But we'll see for stochastic differential utility, it actually causes more problems than it solves. So what we're going to do is we're just going to ignore that. And we can do this because by scaling by some deterministic value at each time t, we're not actually affecting our preferences. So because it's just a linear scaling, we're just going to be we're still going to have the same preferences at each time t. So for the Merton case, for the time additive case, if we assume that this constant eta subscript m, where the m is for Merton, is positive, then we're going to have a well-defined solution to the optimization problem that I just talked about. And so what you can see here is essentially it's saying that because r is positive, delta needs to be big enough such that the integral is well defined. So if you look at this value here, it's saying that we need to discount enough so that the integral converges. So if we assume this well-posedness condition, then we can actually find that the solution to the Merton problem is given by investing a constant proportion in our risky asset. So here I haven't actually mentioned, sorry. So lambda here is just equal to mu minus r over sigma, which is the Sharpe ratio, or the market price of risk. So our optimal strategy in this case is just to invest in a constant proportion of our wealth in the risky asset, and to consume a constant proportion of our wealth. And that constant proportion is actually just given by this coefficient eta. And then, so if eta m is actually less than or equal to 0, then we can also show that the problem is not well posed. So actually, this condition is minimal in some sense. And so, I mean, if we go back to the, here you go.
So you mean not well posed? Not well posed. Does that mean your stochastic differential utility will become infinity at some finite time? Or?
Absolutely. Okay. So what it means is that so if you consider again, we're just in the Merton case, right? So if we consider the case r less than 1, right? Everything's positive. What it means in this setting is that there are attainable consumption streams that actually give you positive infinite utility, and because there's a few of them, then the problem isn't well posed.
Okay, right, thanks.
And in the case r greater than 1, then we actually find that every single consumption stream gives you negative infinite utility, which is in some sense even worse.
All right, thank you, thanks.
Cheers. Sigurd, did you have a question as well?
Yeah, so just a curiosity question. So maybe I missed this. Your delta has to be positive?
So our delta doesn't have to be positive. No, so I mean,
but yeah, if it is negative, easily, you know, this NM becomes a negative too, right?
Yeah, so I mean, we do need that this eta m is positive. Otherwise, we can, as I said, we can come up with positive infinite. But the discounting factor, if we suppose that actually r is small enough and lambda is small enough, then actually we don't need delta to be positive at all. And this is something that some people assume in the literature because it allows certain arguments. But when we investigated the Merton problem last year, we actually managed to remove that because it's not relevant to the maximization problem.
You mean R big enough, or because if R is small, then the second summand of eta m becomes.
Okay, so if we think about this case R less than 1 again. So if your financial market had a negative interest rate and this was small enough, then again you'd find that this term here is positive, and so you could just set delta equal to 0, for example, or slightly negative. And then in the case r greater than 1, then it's it flips around.
So negative interest rates bring in constraints to the theory in a way, right? So that's what we have right now is not good for this. Because we have
so I mean,
now.
Exactly. So I mean, we don't assume that interest rates are positive. We don't assume that the discount factor is positive. All we assume is that this eta is positive, and we show that if it's not positive, then actually the problem isn't well posed.
Yeah, interesting. Yeah, thanks. Yeah.
So, whilst a lot of you have probably seen this form of time additive discounted utility, you probably haven't seen this other way of discounting. So what we can actually, or what some people consider, is they will introduce what's called what we call the difference form of constant relative risk aversion utility. So if we assume that C is uniquely evaluable, then we can actually define this uniformly integrable martingale M. So because C is uniquely evaluable, then necessarily this integral here is going to be an integrable random variable, and when we take the conditional expectation, it's just a UI martingale. And if we remember that here, that the value processed at time t is just equal to the expected value of the following. And then, so what we're going to do is we're going to up count by delta t, and we get the following stochastic differential equation for v tilde, which is the upcounted thing. And then, okay, so now this is pretty dodgy, but we're going to integrate and we're going to take expectations, and we get that v tilde is equal to the following. So we're integrating between time t and time infinity, and then taking conditional expectations. And obviously, okay, so we can't necessarily take conditional expectations because this thing is probably just a local martingale. It's definitely, I mean, there's nothing to say that it's a uniformly integrable martingale. And also, I mean, this integral here at the bottom isn't necessarily well defined. But suppose we can do that, and this object is well defined, then we could start out by defining our utility as the solution to this. So if we have this difference form of the aggregator instead, and we actually find that if we did define our utility like this, so it does restrict our class of consumption streams that we can actually evaluate. It makes it strictly smaller, but if we've got a solution, which is a solution in this sense, then it is also a solution in the other sense. But the opposite isn't true. And you can see why this would happen, right? Because it might be the case that this term is plus infinity and this term is plus infinity. So keeping this in mind, now we're going to go and look at the stochastic differential utility. So this is going to have a bit more of a complicated form, but we're going to see that it does reduce to discounted expected utility. So provided that b is greater than 0, so okay, b here is just some constant, and it doesn't matter, it's just a scaling factor. So we could take b equals to 1, for example, or anything else. But if it's negative, then it actually changes our preferences and says that we prefer less consumption to more consumption. So it has to be positive. R is going to be equal to the coefficient of relative risk aversion that I introduced before. And it's again, it is positive because we've got a risk-averse agent, and S is going to be equal to the elasticity of intertemporal complementarity, which is this measure of how averse we are to our processes varying over time. And then we're just going to define rho to be equal to S minus R over 1 minus R. So if you think back to the time additive discounted expected utility case, then I said before that R is going to be equal to S, right? So in this case, rho is just going to be equal to 0 because this first the numerator is just going to disappear. So given these parameters, we're going to define the difference form of Epstein-Zin stochastic differential utility aggregator to be given by the following. And this sort of, I mean, it looks pretty different to the time additive case, but again, you can check if rho is equal to 0, this term disappears, S is equal to R, and this disappears, right? So this is just the difference form of time additive discounted expected utility that I mentioned before. And as in that case, we expect that this might present us with some difficulties because of the integrability. And then also we're going to introduce this new form of stochastic or Epstein-Zin stochastic differential utility, which has the aggregator given by the following. So now what we're doing is we're actually doing the discounting in front of the consumption, right? So we're doing the discounting by using e to the minus delta t instead of by subtracting this part of our value function. And so we're going to see the same sort of behavior happening, right? So if we consider the difference form of the aggregator, so again, we're going to use, these are going to be v tildes. But that doesn't really matter, to be fair. So if we were to define Epstein-Zin stochastic differential utility by this, then we're going to have the same issue, right? That this term here might be equal to plus infinity, and this term here might be equal to plus infinity. So they're always going to have, you can show that both of these terms are always going to have the same sign, but they might get really big, and so this integral might not be well defined. However, if you consider the differential form instead, so if we cross out this term and do our discounting in front, then because this integrand takes only one sign, we're always going to be able to define the integral on the right hand side here. And also it's worth noting that the integral is always going to take the same sign as 1 minus s. So sine of, hey Gertchen.
Hello, hi Joe. Yeah. So I was wondering, does this difference form and the differentiation form, there are any connections or they are equivalent?
They're complete. Well, they're equivalent in the sense that if you have a consumption stream in the difference form and you can evaluate it, then you can evaluate it in the differential form, and it gives the same preferences, right, over all the consumption streams you can evaluate in the difference form. However, there are some consumption streams which you can't evaluate in the difference form because of so if you think of anything where any consumption streams where you like oscillate between a really low number and a really high number, then actually this integral isn't going to be well defined. Whereas you can define stochastic differential utility for the differential form. Okay.
So you mean as long as both objects are well defined, then they are equivalent.
Then they give the same preferences. Okay. Whereas this form gives us more consumption streams that we can consider.
All right. Okay.
Okay. So yeah, I mean it's worth noting here that the sign of the value process at time t is always going to be equal to the sign of 1 minus s by just looking at the integrand. And we also notice here that the sign of v is also always going to have the same sign as 1 minus r, because this rho might just be any real number. So that's going to mean that we have to have this restriction. So basically this is saying that the sign of 1 minus r has to be the sign of 1 minus s. Otherwise, you're going to end up having this object here taking a different sign to the right hand side. So it's not going to have a well-defined solution. So briefly, before I go talk about changing numeraire, I'll sort of say why we want to do that. So the only setback to this differential form at the moment is that we do have a time dependence. So if you look at the difference form, there's no t in here, whereas the differential form does. But actually, we're going to show that we can remove that pretty easily by changing the numeraire that we consider. So a numeraire is essentially just a unit of measurement, and go and ask Martin about numeraires if you want to hear from an expert. But so what we're going to do is we're going to consider a simple numeraire, like a deterministic numeraire given by dt is equal to e to the delta over 1 minus st. And we're going to discount our consumption streams. So we're going to consider our consumption streams in the numeraire changed coordinate system. So all we're actually really doing here is just renaming things, but we'll see that it gives us a nicer form of the aggregator. So actually we'll find that if V is going to be Epstein-Zin stochastic differential utility associated to the pair G C, then it's going to be also the same as being stochastic differential utility associated to something else C tilde. And it turns out that something else is nicer. So that something else is this F, and you can see that it doesn't have any time dependence. So to keep in the same, to keep in the same coordinate system for our wealth process, we're also going to discount wealth by d. So we're going to consider x tilde to be x over d. And you can show that if C is financeable from your wealth process X, then C tilde is going to be financeable from your wealth process X tilde. And so what this is saying, or like what the main takeaway from this is that the problem with the parameter combination delta R mu is going to be equivalent to the problem with parameter combination 0 R minus delta over 1 minus S mu minus delta over 1 minus S. And essentially what we're going to do from now onwards is we're just going to assume that delta is equal to 0, and this ends up being without loss of generality. So as long as we are slightly careful about changing back into the previous coordinate system at the end when we give our results, then we can just deal with the case delta equal to 0. And so now our numeraire change problem is just to find the supremum over all attainable consumption streams. Here they're attainable, sort of attainable with respect to x tilde, but again, it doesn't really matter. So this is going to be our Epstein-Zin stochastic differential utility process now. And so that that looks a lot friendlier than, well, both the difference form and the discounted form, because we don't have any time dependence. So to derive the optimal strategy, I'm not going to do this because of time pressures. So that there's two choices. I mean, there's loads of choices, but two choices that you could go for would be to choose a constant proportional investment strategy and a constant proportional consumption strategy. So you just invest constant pi in the risky asset, and you consume a constant of proportion of your wealth. And then you find that your wealth process ends up being geometric Brownian motion, and then you can just solve this thing explicitly because C is equal to some geometric Brownian motion. And you just maximize that. Another choice is just to formulate the Hamilton-Jacobi-Bellman equation, and then you solve it and you find the value function and the candidate optimal strategy with it. But I mean, essentially, as you'll see in a second, we end up getting that the optimal strategy is fairly similar to the Merton problem, except for we have we can see where the risk aversion comes in and where the elasticity of intertemporal complementarity comes in. So provided this this eta is greater than 0, so I'm just going to briefly recall what the Merton eta was. So it was, if we consider the Merton eta in the discounted coordinate system, so delta disappears, then it's going to be equal to this. And here again, lambda is just equal to the Sharpe ratio. So you can see that the R stays inside the brackets, but then there's the elasticity of intertemporal complementarity is going out the front. And then given that this coefficient is positive, then the maximum is given by, so we invest a constant proportion into our risky asset, and actually this is the same constant proportion that we had for discounted expected utility. So our introducing the notion of the elasticity of intertemporal complementarity doesn't actually come into how we choose to invest in the risky asset. It's only our risk aversion, which is kind of interesting. And we are going to consume a constant proportion of our wealth, eta times x. And then here's the value function, but it doesn't really matter what that is apart from in the proofs, and they're going to be pretty light. So to prove verification in this sense, we're going to have to introduce a couple of notions. The first of those is going to be a supersolution. So a supersolution associated to an aggregated G and a consumption stream C is just going to be a CAD lag adapted process W, such that the negative part is uniformly integrable, and for all s and t positive, s less than or equal to t, w satisfies this equation here. So it's greater than or equal to, ws is greater than or equal to the conditional expectation at time t of the following. And if we were to consider a utility process, then we could show that actually this is satisfied with equality for a utility process. So in some sense, a supersolution is something that is above the utility process, which kind of makes sense. And also anyone that's familiar with the BSDE literature will recognize that this is pretty similar to the notion of a supersolution for a BSDE. And then you also have this transversality condition, limit of the expectation of WT is greater than or equal to 0. And then a subsolution is very similar, except for it's sort of below a solution. So this inequality flips sign. And then we also, so this is the key part, right, this inequality. But then we're also going to have that the positive part processes UI, and that the transversality condition becomes lim sup of the expectation is less than or equal to 0. And you can show that if something is a subsolution and a supersolution, that it is the utility process associated to C. So we want a comparison theorem. For BSDEs, you always have this comparison theorem for sub and super solutions. So we're going to make a couple of assumptions on our aggregator G. The first one is that it is increasing in consumption, which is a perfectly fine thing to assume, because we essentially want our utility to be increasing in consumption. That's something that we think a rational agent should have, but we also are going to assume that it is decreasing in V, which is kind of a less desirable property to have, and that's important for making the mass go through, but doesn't have economic significance. And that's going to correspond to the case rho less than 0. And actually, this is the case that's studied in all of the Epstein-Zin SDU literature. And if this is if this doesn't hold, then we're actually in the case where we have multiple solutions associated to any consumption stream. So this is a bit of a delicate case, but I'll talk about that at the end. So we are going to have to assume this, but there's not really anything we can do about that at the moment. And then provided these two things hold, so we're decreasing in, provided that we are decreasing in V, then we have that a subsolution is less than or equal to a supersolution. And I'll just give a brief sketch of how that argument should go. So suppose that there is some time t such that the subsolution is greater than the supersolution, and then let tau be the first time that it is less than or equal to it. And then assuming that tau is a bounded stopping time where you possibly need to use some localization argument, we can show, so this essentially comes from the definition of a sub and supersolution. W1t minus W2t is less than or equal to this integral here. And because of the definition of tau, we're going to have that this first term is less than or equal to 0. So that also, we need that W is Cadillac here, and because for all times less than tau, we have that between t and tau, we have that W1 is greater than W2, and because G is decreasing in V, we have that this second term is less than or equal to 0. So you have this thing's less than or equal to 0, this thing's less than or equal to 0, and you end up with a contradiction, right? Because we assumed that it's positive, but actually it's got to be non-positive. So I'm going to skip these proofs, but essentially, as a corollary of this theorem, we can show that all evaluable strategies are uniquely evaluable. So that is actually saying here that we have equality of these two sets when rho is negative, which is really nice. So we don't need to worry about having multiple solutions in this case. And also we have that utility processes are increasing in C. So this is again something we want to have, that more is better than less in some sense. So I'm going to very, very briefly go through how we prove existence of stochastic differential utility, and we note that that V is the stochastic differential utility process, or the Epstein-Zin stochastic differential utility process associated to C, if and only if it's a fixed point of this operator FC. So I mean, you can see that, right? This is the right-hand side of our SDU equation. And so V is a utility process if it's a fixed point of FC, and a consumption stream C is a variable if FC has a fixed point. And we actually show the following existence result, which we actually show something a bit stronger, but this will do for our purposes. So if C star is our optimal strategy, so it looks something like, well, it's a geometric Brownian motion. And if C is bounded above by some constant times our optimal strategy, then FC has a fixed point, and consequently we can assign a utility to C. And then, okay, so this is quite a good result. At the moment, there are very few existence results in the Epstein-Zin stochastic differential utility literature, and this is possibly the strongest. But what we want to do is we actually want to go one step further and say, okay, so what if it's not bounded above by some constant times our optimal strategy, because that's still kind of restrictive. So what we're going to do is we're going to introduce a generalization of the utility process. So if G is an aggregator that is increasing in C and decreasing in V, then we're going to define script E. Hey, Gertchen.
Can you go back one slide?
Yeah.
Yeah, about your condition. Right? So this C star is not known beforehand. Right?
This C star is
the optimal consumption. Right?
Yeah, it is. Well, I mean, the C star, I guess at the moment it's our candidate optimal consumption. So it is just a geometric Brownian motion, but we can say the properties that it has. Because, I mean, it doesn't need to be I mean, it's convenient that it's our optimal consumption, but it is just a geometric Brownian motion.
Okay, my understanding is this C star is also part of your solution, right, of your SDU, because when you solve SDU, you also get optimal consumption.
Yes. Yeah, so I mean, okay, but it could be, we could just, before we've solved SDU, we could just, we've got this candidate C star, which is just a geometric Brownian motion. So what we're saying is if C is bounded above by some constant times geometric Brownian motion, then we've got a fixed point.
Okay, and after you got this fixed point and you got this optimal consumption, you can verify indeed that this satisfies your condition. It
is actually the optimal consumption, yeah.
Okay.
So what we do isn't actually this either. We introduce a class of processes which is much larger than just geometric Brownian motion, but it wouldn't make for a good presentation, I don't think.
Okay, right, thanks.
So we want to generalize the utility process. So provided we have things that aren't bounded above by this geometric Brownian motion, we want to still define a utility associated to it. So we're going to assume C inc and V dec again, and let script E of G just be the monotone limits of sequences which are evaluable. And so we can let Vn be the utility process associated to each of these Cn's in the approximating sequence, and we can define this limit because it's going to be a monotone limit, and we know that V is increasing in C. And so we have the following theorem, that this V actually exists, it's unique, and it is independent of the sequence that we've chosen to approximate it with, that we've chosen to approximate C with. So Cn tends towards some C. So you pick the C, and then you can find an approximating sequence. And what we're going to do is we're going to call this V the generalized utility process. Because in some sense it's a generalization of the utility process. And actually, if a consumption stream is evaluable in the sense that I previously said, then this V is going to agree with that, the utility process that we've associated before. And then also this V has like lots of nice properties, so it's increasing in consumption, for example. And we actually find that these geometric Brownian motions are just going to be, we're going to be able to approximate any consumption that we want by these processes. So we get this following corollary, which is if C is a non-negative progressively measurable process, then there's a unique generalized utility process associated to this pair. And that's really nice. So that means that we can actually have a meaningful utility that we can associate to any consumption stream, so any non-negative progressively measurable process. And we can show that, so in the case that R is less than 1, this ends up being the minimal supersolution. And in the case R greater than 1, it ends up being the maximal subsolution. So it's actually also like a nice process. So what we want now is we want to just consider the problem without any evaluability constraints. So because we've got this generalization of the utility process, we just want to optimize over attainable consumption streams. And we actually have this following verification theorem. So provided that all of these constants are positive, provided that eta is positive, again, this is actually, we can show this is the minimal condition we need. So if this is violated, then again you have these positive consumption streams which give you positive infinite utility, or everything gives you negative infinite utility, depending on the sign of 1 minus r. So given this is satisfied and rho is less than 0, then our optimal investment consumption strategy is actually optimal, or so our candidate optimal investments consumption strategy is optimal, and the value at time 0 is just given by our candidate value function of x. So this is quite like a standard verification theorem. And I'll just quickly go through the steps of that. So you show that the candidate value function satisfies the HJB equation. If you've derived it via the HJB equation method, then obviously that's going to be the case. Apply Ito's lemma to v hat of your wealth process x, and what you're going to do is you're going to find that because it satisfies the HJB equation, that v hat of x ends up being a supersolution associated to the pair FC. And then because it's a supersolution, we have that at time 0, v hat of x is greater than or equal to v naught of c, because v naught of c is just a utility process, which is a subsolution, and we just use the comparison theorem. And then under our optimal strategy, the supremum in the HJB equation is achieved, and we find that v hat of x is equal to v naught of c star. And then, so this first equality just comes from optimality of c star. This inequality comes from this, where we just take the supremum over all consumption streams, and then we have that c star is an attainable consumption stream. So obviously the supremum is greater than or equal to it, and you have the result. So finally, I'm running very short for time, but I'll just chuck in a couple of what the next steps could be. So at the moment, the thing that is conspicuously absent is the case rho in 0, 1. So this is because you want it to be decreasing, and you want the aggregator to be decreasing in V. But that's what we're going to work on next, and I think that that our method should hopefully work in this case as well. So we should be able to get a verification theorem then. Except for we're going to have we're going to have to be a bit more careful because, as I said, there's multiple utility processes associated to a consumption stream. So we need to, in like a meaningful way, explain which is the correct utility process associated to the consumption stream. Another thing we could do is just prove finite time horizon existence. So, as I said, the existence results in the Epstein-Zin stochastic differential utility literature aren't that great at the moment. So I think if we wanted to, we could probably generalize our result to the finite time horizon problem and get a strong existence result. And then also, okay, maybe consider some generalizations. So what about if we change the financial market? What about if we add transaction costs, stuff like that? So thank you very much for your attention. I hope you enjoyed that. And if anyone's got any questions, I'll stay around for a bit.
All right, thank you. Thanks. So Sigrid, you have questions?
Yeah, just a quick one. If you could go back just 2-3 slides, please. Yeah, this one here, the outline of the proof.
Yeah.
So this V hat, right? It's a limit, isn't it?
The
V hat.
This is the limit here, right?
No, the V hat, your candidate value function V hat.
Yeah.
No, not there on the first line.
Yeah.
This is a limit, isn't it?
It is
because it's a generalized,
yeah.
right?
So the candidate value function isn't a limit. We've got an explicit form for the candidate value function, but this
because it's your optimal one. I see.
But this is a limit. So that's a very so I was a bit cheeky when I talked about the comparison theorem.
Okay, that justifies my question, clarifies, because I was wondering why do you have regularity to apply Ito's lemma? But this is a specific one.
Yeah.
Right, okay. Yeah, that's right. Okay, I'm happy. Yeah.
Yeah. So actually, you do. You don't actually have that. This is a solution or a subsolution, but you have that it's the minimal supersolution. So obviously, because this is a supersolution and this is the minimal supersolution, then you end up having this inequality. But it is actually, it does introduce some issues.
All right, thanks.